All right, everybody, today I want to talk about vector addition. So as we learned in chapter 1, vectors are quantities that have magnitude and direction, like say force or velocity or acceleration or displacement. And when we add them together, we need to not only consider their magnitude, but also the direction and how they combine. So when we do typical scalar addition, what we're doing is walking along a number line. And when I add two positive numbers, I continue, start at the first one and walk more positively out. So start at the first one, walk more positively out to the second one. If I had a negative number, I go out here and then I walk toward the negative side. So if my first one's positive and then negative and positive, negative and negative. But now since I have these two quantities and they're not on a number line, I need to consider how I'm going to deal with this particular situation. So the first, probably most obvious way to add two vectors is the graphical method. So if I were to create a scale, so say 10 meters per second is equal to 1 centimeter, and draw two vectors that represent velocities, I could say, well, if I want to add a plus b, what I can do is I can walk out a, and then I can walk out b. And since vectors maintain their properties as long as their length is constant and their angle with respect to our coordinate system, which in this case 0 degrees is over here, is constant, I can just take this vector and I can move it up here like this. So now I've walked A and B on my paper and I can draw C. C would be the sum of A and B. And A has some angle alpha, B has some angle beta, and that angle is preserved here with respect to the x-axis. And C would have some length, which I could get and then convert by the scale back to its velocity, and some angle, gamma. So in this way, I could always add vectors, but it has some limitations. So what are those limitations? The limitations are, well, I can only do this so accurately because I'm using rulers and I'm using protractors, and it's time consuming, and I really don't have a lot of control over the process. So if I want to do it more accurately, I have to do it in an analytical manner. So let's begin to think about how we could introduce an analytical method into vector addition. So the first and easiest way would be to think about, well, what is vector A? Well, I can either walk vector A along A at some angle, or I could go out some x and up some y to end up at that position. Same thing with B. I could walk B at some angle, or I could walk some negative x and some positive y. So I can think about my vector either as a magnitude and a direction or as unit vectors along perpendicular axes. So what would that look like? Well, in that case, I would have my A and I'd have some AX, which is the unit vector for A. I have some AY and the unit vector for Y, and some BX and some BY. Well, now I'm on a number line, two number lines, but still a number line, all right? And that would mean that I can add AX's with BX's and AY's with BY's and hopefully get my C. So if I do that, I start at the origin and I go to the right AX and to the left BX and I go up AY and up BY. I end up at this point right here, which is my C. And now when I draw my length and my angle, I get the same angle and magnitude as I got with my traditional graphical method. So what I want to say is that I can then use trigonometry if I know the magnitude and direction to determine all of my component vectors. So in this case, I could, for A, with my alpha down here, I would have a sine theta and a cosine theta, and then I'd have B cosine theta and B sine theta, and that would give me my component vectors. Then I can add them and get the component vectors Cx and Cy. So let's try that with some actual numbers. So let's say I have a 30 Newton force at 30 degrees from the horizontal. That's my green guy down here. And I have 120 Newton force at 15 degrees clockwise from the vertical. So This is just a sketch, so I want this one to be much longer than this one because it's 4 times as big. And then that 15 degrees is 15 degrees from the vertical. So now I've got to break these down into their component vectors. So how am I going to do that? Well, let's make some right triangles. So first I can say, okay, well, I've got this pretty obvious triangle to work with here. And I've got this pretty obvious triangle to work with here. All right, so what do those look like? Well, this guy's pretty easy. If I call this vector A, and he has a length of A, he would be over here A sine 30 degrees, and down here A cosine 30 degrees. For vector B, it's a little bit more difficult because I gotta say, well, this 15 degrees isn't inside my triangle, so where is it? Well, it's this angle right here, actually, right? Why is it this angle? Because I have 2 parallel lines, the y component of vector B and the y-axis cut by a transverse, and that means that opposite interior angles are congruent. So I got to remember a little bit of my plane geometry from way back in the day. And knowing that this is 15 degrees, I can then say that, well, this is B cosine 15 degrees, since it's up, and this would be negative B sine 15 degrees. So why negative? Because it's on the negative x-axis. So I draw these pictures not just for my own edification, but because it allows me to double check all my work and make sure that my result makes sense. So now I've got to break these vectors down into their components, which I can do by saying, all right, I've got AX and AY, and that is 30 newtons cosine 30 degrees and 30 newtons sine 30 degrees, which is 15 newtons and 25.98 newtons. So I should really put a 0.0 here because I always want to have at least one more significant digit than I've given. And now I can look at B, right? And BX would be negative 120 newtons. Now it's opposite, the 15 degrees is opposite the x sine, so I'd say sine 15 degrees, and BY would be 120 newtons cosine 15 degrees. And that gives me values of negative 31.1 newtons and 115.9 newtons. So my total vector C, okay, would now just be CX would just be AX plus BX. And that is negative 5.12 newtons. And CY would be AY plus BY, which is 15 newtons plus 115.9. Which gives me 130.9 newtons. All right. So I now have my vector C in component form. So I can say, well, how do I get it back into that vector magnitude and direction form? Well, let's draw vector C. So here's vector C. And we know that it has this little negative part here and this big positive part here. So I again have a right triangle. And I know the values of the right triangle now. Okay, so the y value is 130.9 newtons, and the x value is negative 5.12 newtons. So to find the magnitude is always the hypotenuse. So C. So that means C is just equal to cx squared plus cy squared square root by Pythagorean's theorem. Got to remember this is in parentheses. Take the square root of all of that, and I get 131 newtons. Now to find that angle, I got to be careful. Okay, so I could say, well, let's find this angle right here. And then rewrite it in terms of what I know. Okay, so this angle, we'll say theta, is equal to the arctangent of 130.9 over 5.12. Okay, and I use all positive values. And when I do that, I get 87.7 degrees. Okay. Now, if I want to write it in the same way as the other ones are written, I would say, well, what is it from the positive x-axis? Well, that would be 180 minus 87.7 degrees, which is 92.3 degrees from the positive x-axis. But I could equally say it's 87.7 degrees from the negative x-axis, or 2.3 degrees from the vertical. The other way, and when you're answering questions on the homework or in a test, I would tell you which way to say the angle, or I would accept all possible answers, okay? The other thing that the book likes to talk about is declinations. So in that case, we would say that x-axis is lined up east and the y-axis is north and south. So I could say that it's 92.3 degrees north of east. So I start at east and I rotate toward north. Or I could say it's 87.7 degrees north of west. So I go to the west and I rotate toward north. Or I could say it's 2.3 degrees. Well, now I want to start north and rotate west. So west of north. All right. So that's vector addition in a nutshell. Now, because I talked about vector addition, I also talked about vector subtraction, because when I subtract things, all I'm doing is adding the opposite. And the opposite of an angle is just the angle that's 180 degrees away. So if I say that A is 20 newtons at 30 degrees, minus A would be 20 newtons at 30 plus 180, 210 degrees. Now, if I end up over 360, I have to choose the equivalent angle. So if I'm over 180, say at 190 degrees, the opposite of that angle would be at 10 degrees, or if I'm at 270 degrees, the opposite of that angle would be at 90 degrees, because I'm never going to deal with an angle that's greater than 360 degrees. And I've got to remember that when I go rotations around a circle, I go from 0 to 359.9999999, and then I start back over again at 0. Okay? All right, I hope that was helpful. If you have any questions, please ask them in class.